A wire is placed in a magnetic field which is directed to the right. The wire carries a current directly into the page. Which of the following is the direction of the force on the wire? Okay, so I use the slap rule. We have a current, which is a conventional current, directed into the page. So we point our thumb into the page. We point our fingers with the field. This is our right hand. So it's going to experience a current downwards, which is along D, which is there. You guys have used the Fleming rule. You can use that. I use the slap rule. I think it's simpler. The temperature of an object is minus 153 degrees Celsius. The temperature is raised to that. What is the temperature change of the object? So delta T is equal to Tf minus Ti, which is equal to, well, the final. It's raised. So that's 273 minus negative 153. So it's going to be, what, like 420? 26? 426? There we go. In a double slit experiment using monochromatic light, a fringe pattern is formed on the screen. A decrease in which of the following will increase the separation of the fringes? Okay, the equation generally is n lambda equals d sine theta, or n lambda equals dx over L. Okay, so we want to increase the separation of the fringes, so we want to get x up. Okay, if we decrease the wavelength, x will go down. If we decrease the distance between the slits and the screen, L, if we decrease L, x will also decrease. If we decrease the separation of the slits, then x will increase, right? Because if we rewrite this equation as d is equal to n lambda L over x, then we can see that if we decrease d, x will increase. So it's the separation of the slits. Okay, monochromatic coherent light is incident on a narrow rectangular slit. The diffracted light is observed on a distant screen. The graph shows the intensity. The width of the slit is reduced. Okay, if we reduce the width of the slit, it means the pattern is going to spread out. Which graph shows the intensity of light observed? The original diffraction pattern is shown with a dotted line. So we're going to get a pattern that is spread out. So it's going to be either A, so it's going to be wider than the original one, or it could potentially be D. If you look really carefully, that one is also spread out. And so which one is going to be the correct one? Well, the intensity, would that drop in this case? I think the intensity of the central peak, I mean, we are going to have less light getting through directly ahead. So I think D is the correct answer. In any case, it's either A or D. I have a suspicion that the original marking scheme was wrong with this one, so just double check that you got that one, that you got credit for that one. Okay, 25. Which graph shows how velocity v varies with displacement x of a system moving with simple harmonic motion? Okay, so we can easily test what should happen at equilibrium in the two extreme positions. At the two extreme positions, so when x is big and positive and x is big and negative, we should have 0. So it's either this one, oh, in fact, it's got to be that one. That's the only one. Oh, it could be C. But in C, the velocity is also 0 when it's going through equilibrium, which is not the case, so it can't be that one. In this one, the velocity is not 0 at the greatest displacement, so it can't be that one. And the same with B. With B, the velocity is really big at the extreme position, so it's 0 at equilibrium, so it can't be that one. It's got to be A. Okay, 26. An object undergoes simple harmonic motion with time period t and amplitude 0.5 meters. At time t equals 0, the displacement of the object is a maximum. What's the displacement of the object at a time 3/4 of a period? So it starts off, so if we think of a mass bouncing horizontally between this position and this position, it's going to start off here. After 1/4 of a cycle, it will be there. 2/4 of a cycle or half a cycle, it'll be there. 3/4 of a cycle, it'll be there. And so it should be back at equilibrium, so it should be at D. 27. Light of a wavelength 600 nanometers travels from air to glass at normal incidence. The refractive index of the glass is 1.5. The speed of light in air is this. Which following identifies the speed of waves and their wavelength in the glass? Okay, so they're going to slow down in the glass, so it's going to be slower than C. It's also going to be shorter wavelength than C. So it's got to have a smaller speed than C and a shorter wavelength, so it's got to be D. Because as the wave fronts enter the slower medium, they're going to get bunched up closer together. 28. Unpolarized light of intensity I0 is incident on a polarizer. The polarizer is rotated by an angle theta about the direction of incident light. Okay, it's unpolarized light to begin with. Then no matter how we shine it at the polarizer, we're always going to get half of the intensity on the other side, because we're going to eliminate all of one component, and the light can always be split into two components, so only half the light's going to get through. So it's D. If this were polarized light, the answer would be different. If we were shining polarized light at the polarizer, then when it's in line, we would get all of the incident light getting through, and when it's exactly perpendicular, then we get 0. So then it would look more like B. But in this case, that's not true because we have unpolarized light shining at the polarizer. Okay, and finally, three wires P, Q, and R carry equal currents directed into the plane of paper, which correctly identifies the direction of the magnetic force on wire P. Okay, so here we have a field that goes like this into the paper. We have a field that goes like this and like this and like this. And so in which direction will the wire experience a force? If they are going in the same direction, it's going to get pulled in towards X. Okay. The internal energy of any substance is made up of the total random kinetic energy and potential energy of the molecules. Whoops. Okay, so that's the multi-choice. Let me know if you have any questions.